is a home base for these sessions, as well as registration and credential pickup. Film festival selections are screened day and night at 8 different venues in downtown Austin. And Music Fest showcases film more than 100 Austin venues nightly, including 3 special outdoor shows at Vic 5 shores on Lady Bird Lake. The South by Southwest conference schedule has been consolidated to include keynotes, featured speakers, interviews, and other sessions across the interactive, film, and music industries. Conference programming is primarily located at the Austin Convention Center, JW Marriott, and Hilton downtown, but also nearby venues like the Westin, Driscoll, Intercontinental, Four Seasons, Hyatt, and Palmer Event Center. Official parties and networking events take place all.
Okay. All right, so welcome to this session in robotics. I don't know if you have been around, but there will be quite a bit of robotic sessions. So there will be South by. We have famous roboticists in this room right now as well. And I'm delighted talking to this crowd about one of my favorite topics, which is humanoid robotic systems, especially with the question of what is the next wave of human-robot interaction with humanoid systems? In particular, trying to understand and code and develop the hardware for understanding some sort of human emotion, and to a certain point be able to intervene in our daily lives to make us more productive, to make us more healthy, safe, entertained, and so on and so forth. Ultimately, the goal of this area of human-centered robotics is a very developers-oriented session, to the point that I brought my own developers. We honor what the developer is, which is working until 3 a.m. the night before. So we are all in 4 hours of sleep, and I'm proud to say that. Thank you, thank you. These guys work really hard. And I also want to thank many organizations helping with this kind of research. IEEE ultimately invited me to give this talk. And I work at the University of Texas. We all work at the University of Texas. I also co-founded a company. One of the great things about Austin is the fact that it's now becoming a leading city for high density of the startups being created, and the company is Astronic as well. But people here supporting this kind of research are things like NASA, the National Science Foundation, the Navy, and Texas itself as well. All right, so let's move on, and I want to give you a feeling precisely of that, the innovation that takes place, what we do, what kind of weird things we do in laboratories. So here we see us on the left side yesterday at 3 a.m., still working, right, hacking things. And then you go 5 years later and filter by the Innovation Center at UT, which is an institute headed by Louise Epstein, Bob McCall, and Steve Nichols, the 3 great guys at Austin. You find the students becoming co-founders or founders of companies and CEOs. Here's a company that I'm also co-founder. I don't want to make a lot of fuss about it, but the important thing is that the students, they go from the laboratory and they do become heads of companies right away. I know that it happens in many places, but Austin is just at the head of many of these efforts. So as you can see from the pictures, a great focus of our research and products ultimately goes into embodiment, into hardware development, into the real-time systems, comms, actuators, which are ultimately the things that create this kind of lively motions and make robots more productive. Unfortunately, I'm also a contractor for NASA Johnson Space Center. This is the room where the Apollo spacecraft was built in the late 1960s, and we closed ourselves. You can see there are no windows at all. So we were there as a team for 15 months, developing all sorts of machinery and going almost crazy. That's what developers we do, right? And hopefully the payback is this wonderful machine. We developed a lot of the subsystems of this machinery. These are our actuators are called They're called series elastic actuators, high power density. And they are implemented in the torso and in the legs. And they allow you to have this touch sensitivity that is very important for human-robot interaction. When these robots go outside and they start doing work with the astronauts, it's very important the safety dimension. So the robot has to be aware, what we call whole body contact aware, outside and inside to do these operations effectively. We work a lot, talk about developer embedded systems as well, as previously mentioned. I guess that some of you are, it's not only the high level AI, but it's also the comms, the serial communications, the quality of the data and so on and so forth. Very important to pay attention to all these things. And of course you have to go a little bit to the mission specification. So NASA engineers are always in missions. How do we get robots to do what they got to do? And here we blend something called whole body controllers, which run under the hood, that they coordinate all the movement. And then there is a motion planner, which is a semi-intelligent artifact that creates trajectories. Those trajectories can be almost learned or searched at runtime using methods like dynamic motion planning or RT. There's a lot of search. But also we program some of the behaviors to account for the affordances. Ultimately, Kim here, Kim Kampuchen, who's one of the heads of the NASA Johnson Space Center program Robotics, she's able to teleoperate Valkyrie just using one hand. A lot of it is because of the UI, UX, user experience, user interfaces that are dedicated to make it relatively easy, the semi-teleoperation behavior. Now, this is about a couple of years old technology. We're now going to the next wave of mission, and actually some of these guys are PhD students, by the way. They are investigating discovery in the areas of software synthesis, declarative programming, synthesis of behavior from atomic propositions. A lot in the logic domain. We're trying to integrate also with the continuous domain, with the optimal control problems. Maybe I do too much lingo here, but that's what we do as developers. Okay. This program has been quite successful. There are 4 Valkyries. These are Valkyries. On the back of here, we have Robonaut. Robonaut is right now in the International Space Station. It has actually legs, not for walking because there's no gravity, but for grasping. It grasps itself on the International Space Station. Valkyrie has legs. It's designed for a gravity environment like Mars. And it has this small footprint, and it has these 4 sensitive capabilities for going into habitats and equipment right next to the astronaut and making the astronaut more productive. And I think that for me, being at NASA, it helped transform the way I see productivity, because a lot of it we see it in the context of companies or manufacturing, which is not about products for the cost and so on and so forth. But productivity for NASA includes safety, includes comfort of the astronaut, minimizing the time of the EVA, extravehicular activity, and so on and so forth. So when people ask me, do we need a humanoid? Do we need legs? Do we need all these things? My answer is, we don't. What we need to do is make that thing as productive as possible, including the human dimension if it's needed, and the safety and so on and so forth. And if legs allow you to fit in the environment, test ergonomics, be safer, and so be it. But if not, we're going to change the topology. So as developers, we have to be able to operate in this dimension of creating hardware for that specification and generating computational methods, communication methods, real-time methods that can apply to all these series of devices. What else we do? That's again, yesterday at 3 a.m. There's no voice? No sound?
Vending doors have 2 lines.
Oh, I have to switch it over here.
Is reached. Remember, your credential does not guarantee entry into every event, as each event is subject to vending capacity.
Okay, it's a developing session, developing session. But yeah, the volume's on here. All right, so there's no big deal. Press the volume, please. Okay. So that was the kind of process that you see in this kind of research laboratories. Very intensive on testing, very engaged. As a matter of fact, here we have a disembodied upper body, and the upper body is trying to poke the eye of the robot. As you can see, it's very deep, meaningful research. All right, we spent about the whole night doing that. All right, and then we thought we would maximize the number of YouTube videos, which we're going to see if it's going to happen, right, over time. But no kidding, a lot of the researchers here, ultimately they are scientists. That's what PhD is about, for those of you who have PhDs, and that we need to generate discoveries. And the discoveries happen in the physical realm, they happen in the temporal space realm, they happen in the human factors arena. And I think a lot of it also happens in the cognitive arena. It's the fact that as computer scientists and engineers, we're losing fear for writing the equations of internal behavior of the human and using processes that are normally used for the generation of movement and control to actually steer not only the robot, but also the human interaction, the human outcome, what the behavior of the human is going to be. All right? So I create a vision, but these guys know how it works. I want to bring our first developer, Travis, to present how he builds hardware for this kind of interactions. So you have your stuff?
Okay. Hi, I'm Travis Yotto. I'm a PhD student currently at UT Austin. And my background, currently I'm kind of a generalist, spending equal parts in mechanical, electrical, software. I started out in mechanical, and so this is the head of one of our robots, Dreamer, which is sitting on the table right over here. How do we get the proper thing? No, I want to see the table. Oh, well. Anyways, and so the robot Dreamer that you saw in previous slides, here's part of the body over here, and then the head sits on the table. They do connect. The entire system was built as one large piece. Everything, hardware, software, was extremely experimental. It was all new. It was all very immature when it was built, and the original purpose was more or less to prove the technologies used in those prove the abilities of those new technologies that we had built into the system. Now that we've gotten to that goal and we want to build further work on top of it, we decided to strip at least the head down and make it as reliable as possible so that it becomes a more usable, more robust foundation for our future work. So we, let's see, I don't know if we can well, anyways, this is our head with the face off. It has a cosmetic face that goes up front that is on the table right now. But we reverse engineered everything since unfortunately the company that built it for us is now part of Google. They don't answer our emails. So we started out reverse engineering mechanics, CADing everything, redesigning the less reliable parts of the micro mechanisms to improve performance. We redesigned all the electronics. We wrote completely new low and mid-level source code. And since we want to be able to take this system and give it to grad students, give it to undergrad students, give it to even high school students that visit our lab and work with us in the summer, we want to be very, very accessible. And so unfortunately that means abandoning some of the high-performance experiments we were doing in the past. But it also opens up tons of new doors when we can replace bespoke electronics with $15 microcontrollers comparable to an Arduino. And we can replace incredibly expensive CNC milled parts with MakerBot printed parts. Just about the only part we haven't been able to seriously optimize is reducing cost by 80 or 90% is the motors. We're still using very high performance Swiss-made motors. They're just terrific and we don't want to get rid of them. But overall, we switched from completely bespoke system to a mostly commercial off-the-shelf system. We improved reliability by orders of magnitude. We 50% cost reduction overall. It was like estimating if we were to rebuild this today, we could do it for about 1/5 of the original cost. And so that's the hardware side. For the software side, again, the same concept. The original system was completely bespoke, all closed source software. We had access to a few configuration parts of the software, but not the source code itself. So debugging was very, very difficult. We decided to go with completely free open source software the next time around. And any complex robotic system is going to be built in the hierarchy as any really complex software will that needs to be deployed across distributed systems of cloud computing or data centers or anything like that. Backend, the lowest level is running assembly code, mostly for signal processing, interfacing between different components on the head. Mid-level control that does trajectory planning and control loops inside the head is written exclusively in C. Currently, we're using the robot operating system, ROS, as our vision system only. High-level planning, all the whole body control, and the human-robot interactions experiments that we'll be showing later on. Those are written just simply in Python. Essentially, assembly gives us, of course, the lighting we need for completely deterministic stuff. C gives us also extraordinary speed on the parts that hopefully won't change too often, and Python allows us to write entirely new experiments over the course of a few hours. And so anyway, this is what we're up to at this point. We have the head transition from the original state where it typically would run for an hour and then spend a month in repair mode. And now we're to the point where we can literally just plug it in and flip a switch and run anything we can write that day. We can hand it off to undergrad students, we can hand it off to high schoolers and let them deploy their code in hours. Okay, so next, here's some of the concepts.
Okay, well, thank you. So, a couple of important things. As you can see, the model of Dreamer, the face of Dreamer is very cartoon-like, and we decided that in purpose. Actually, we look at Japanese anime just because I personally grew up with Japanese anime and got very inspired. Looking at some of the work of Miyazaki, for instance, and others, where the traits are such that they give you a sense of comfort, but without being threatening look and feel. And also it has a smart look as well. So all this is very important because these robots ultimately are going to be operating around us and helping us in our homes and cities or in the space, even more importantly. So it's important how it's going to look like. And that ultimately resulted on this look and feel. I think we captured it pretty well. If you go to other sessions here, you're going to see more anthropomorphic, more human-looking like devices. That's called the uncanny valley, where you can be either on the cartoon side or the very realistic side. But if you go to the very realistic side, you have to be very precise about the movements, the look, the texture, the coloring, and that requires a significant higher investment at all levels. And you're just playing a different type of game. Our take is that you can be on the other side of the uncanny valley, but rather than on the look and feel, you can be on the emotion, on how do you connect, either as a connected interaction or a disconnected interaction if you want to mimic some of the awkward behaviors of humans. We're going to have a little bit of a talk on that pretty soon. But so much we've seen the building a robot, a human-centered robot. So the next thing that we need to do is take into account how to design trajectories. And for that, we go to foundations of robotics called kinematics. In kinematics, we consider the constrained movements of the eyes and the ears. We have 9 degrees of freedom. And how they relate to the objects that we look outside, people, for instance, or things moving in the environment. And we do that through using these metrics, very convenient. When we express it in differential form, is a linear system where we can relate external coordinate systems with the joint coordinate systems. And later on, we can use those for control of all the degrees of freedom. Okay? So now that we have We have built ahead, we know the transformations for the joint coordinates to look at things. We have to tell the robot to look at something. And for that, we need 3 coordinate systems. We need the inertia coordinate system at the base, we need the head coordinate system, and we need the desired coordinate system that we want to look at. So we want to express the error of what we are to what we want to look at. We express that in a rotational matrix. This is something called, it's pretty simple to compute it. It's called directional cosines. And we express it by computing the rotation from the body we want to look with the warframe, the rotation from the head to the warframe, and expressing that, multiplying them, and we obtain an algebraic error that ultimately that's going to go to a controller, and that's going to allow you to track the people in movement in the environment. Okay, so far so good, but then we might not get what we want, and we see a lot of the robots that they are very shaky. As a matter of fact, one of the most famous robotic systems in AI is called shaky, back in the 1970s, 1960s, 1970s. So jerk is a very important problem. In industrial robotics, jerk results in poor performance, so you end up hitting your manufacturing environment and breaking things. In human-robot interaction, it's very important because if you jerk, you're going to look creepy. Perhaps because when we are sick, we have the diseases, sometimes we jerk, and that is seen as a weakness, perhaps, right? Just a hypothesis. But fortunately, we can encapsulate jerk in the form of an equation because it's the third derivative, the jerk is the third derivative of a trajectory. We have here a position, we have here the velocity, the acceleration, and the third derivative is just this jerkiness, pushing the accelerator and stopping right away, sort of. So we do control policies that will minimize over a time horizon how much jerk takes place on the robotic head for looking at things. And that results on fifth order polynomials. Okay? So these are the fifth order polynomials. Now we need to do something useful, something biomimetic. So what we do is we concatenate behaviors. Let's think about nodding or rolling the eyes. Yes, the eyes and the head, they are different trajectories, and they need to be concatenated with each other. And we see here the effect of using a minimum jerk trajectory. We feed the 3 states at the beginning and the end, the intermediate, and it results in 2 fifth-order polynomials describing our very nicely behaved interactions. Okay, so great. We have the hardware, we have the orientation error, the kinematics, we have the trajectories. Now we have 9 degrees of freedom in the system. We have 4 in the neck, we have 4 in the eye, and all of these is to be coordinated together. But we're not going to create trajectories for every single degree of freedom. What we're going to do is use motivation for our work on space robotics, in which we coordinate the entire multi-body system of humanoid systems using something, a theory that I co-developed called whole-body controllers. In there, you create trajectories only for a few keyframe points. For instance, locomotion or manipulation. And those are 2 points. They are not the 35 degrees of freedom of the entire system. And through whole-body control, we can merge them together to get to do these sorts of very complex interactions that we do for NASA, for instance. Okay? We brought this theory to the human. Sorry. Let me go before that. So how does it look mathematically? I know there's a big equation, but it's a constraint optimization problem. Where we have here the criteria, we have trajectories, and here we have accelerations or forces we're touching the environment, or the robot with respect to the environment. And then we have here what we call the multi-body dynamics. It's a model of prediction of how the robot is going to balance and move over time. And then we do that in an iterative manner, such that we create only trajectories for these keyframes, and then we can define what is more important at every given time. So if there's a conflict between multiple trajectories, the kind of the constraint optimization process is going to take care of that conflict. Okay? So ultimately, this kind of theory goes into the head coordination. We see here the 9 degrees of freedom. The eyes, to look at something, both the eyes and the head can look at the same time. So what is the decision? In this case, the head is going straight, and the eyes are kind of rolling to look at things. That would be kind of a sneaky look at something. Okay, we use priorities in a certain way. Whereas in the second one, we see the head creating, the head itself is creating a triangle, a square, but the eyes are looking dead center. So we can coordinate this very sort of human-like behavior using these computational techniques that are important to us for the human-role interaction process. Okay? So this is we're going to see something more sophisticated than this today. It was a half-baked a couple of days ago. And the robot is using all this environment, computation, and hardware in order to create a good human-role interaction process. All right, so we have a lot of the engine in hand. We have a lot of the down-to-earth mechatronics, kinematics, this very kind of old theory. But these robots, without more than this, they are lifeless. We need to bring them to life. And we believe that to bring them to life, we have to understand what behaviors are, what behaviors of human around are. Fortunately, this is not science fiction anymore. We go to behavioral scientists, people like anthropologists or psychologists or pedagogists, to develop theories of human behavior. Things like self-efficacy, which is motivation, or competence, or trust, computational model of trust, or empathy, okay? Not in a holistic manner. We're not pretending to reverse engineering the brain. We wish we could, but we do it in a very local way. Can we estimate the motivation of somebody to do exercise today, or to eat something, or to not eat something and do a diet? Can we estimate the motivation of a student to do the homework? But more importantly, if we estimate it and we predict it, can we intervene over the process? Can we change the mind of the person to that particular process to make things more effective and productive? Okay, so we use social cognitive theory, and then we go to the field of applied mathematicians and control theories. I belong a little bit to control theory community, which are fearless mathematicians. That they can go to any process that can be explained with words and can develop the mathematics of the process. Sometimes I call it the equation of empathy, or the equations of love, right? If you go to the extreme, right? Can we computationally create those equations, and what kind of models we can use? And sure enough, this body of work that is very scientific and very serious about attempts to do that. Obviously, these theories are as good as we feel that they affect our emotions, okay? But we attempt to do it. So here we see something used in the social cognitive theory, behavioral scientists mixed with applied mathematicians. It's a system where we're trying to estimate the mutual trust of robots on the humans for navigating as close as possible based on historical data, okay? So the robot has a model of, my student calls it mental comfort, okay? The robot has not really a mental process, a fake mental process, which depends on an estimation of the comfort of the human, based on what? Based on the emotions of the human, based on what? Based on our observations of parameters such as biometric parameters, sweat, heart rate, movement, frequency of the movement, and so on and so forth, right? It's affected by physical safety, how close, how erratic is the movement itself, emotion, trajectory, and also how productive the human is on executing the task. And all of this is merged together into this interconnected network. Each of these things are not neurons, they are actually dynamical systems. They're first order dynamical system tanks. They go up and down. We don't change our trust in a moment, it takes time. And ultimately it delivers mutual trust, which governs the movement of the robot. So this is kind of a big picture theory, but we need to execute it in real systems. So I'm going to have Orion, another developer, who actually takes these crazy ideas and tries to give them shape and body.
All right, hello, my name is Orion. I'm another PhD student here at UT, and this is a simple model that we created based on these socio-cognitive theories. And the idea behind this model was to govern the eye contact behavior of Dreamer, to either build connection or be awkward when you're around people. So we were wondering if we could use this theory to actually implement this in a real robot. This is simple because we just have two states. So our two states are connection and awkwardness. And we have feedback systems, and we model it as a linear dynamical system where the states can be thought of as water tanks, and you have these tanks draining into one another in a simple fashion to govern the behavior. In this way, we can design behaviors by identifying the types of characteristics of the behavior that we care about. So in this case, we felt that some of the things that influence awkward behavior would be no mutual gaze or staring, and some of the things that would build connection would be eye contact between the human and the robot, or from the robot to the human. So moving on to how we actually implement this in a real system, it all depends on how you want to design the cost function. And so you can actually balance different parts of the behavior with different weights to get different behaviors out. So when we care about building connection, we weight that more heavily. When we care about building awkwardness, we can weight that more heavily. So this shows some of the output of what our system produces. And in this particular case, we're showing the results for building awkwardness. You can see in the second row, we show the robot looking at the human in red and the human looking at the robot in blue. And because it's building awkwardness, it's actually they're counter phase. So the robot notices when the human looks at it and it looks away. And when the robot notices that the human is looking at it, so it avoids that eye contact. And then you can see also at the end here, it notices that it has an opportunity to stare. And so it actually maintains eye contact for an extended period of time to the point where it becomes awkward. This is a maximizing awkwardness behavior. So we can actually use this as what we don't want to do in most cases. Here we're showing some of this awkwardness maximizing behavior. So just completely avoiding eye contact with the human. And it works pretty well. It's fairly awkward if you're trying to talk to them. And so we actually performed experiments with the students at UT and did experiments where they're interacting with the robot and measuring how comfortable they feel in these interactions. And we can use that feedback to kind of tune our models. So I'm going to hand this off to Stephen, and he's going to talk about some of the ways that he's extending this to other emotions and other models of behavior.
So I'm Stephen Worthington. I'm also a PhD student at SXSW. And what I want to show is that these models that we develop for eye contact and awkwardness and connection building extends to other domains of human-robot interaction. In this case, Dr. Sennis mentioned earlier that we care about productivity. And we want to make robots very productive. But also, we want to make them very empathetic. We don't want robots to accomplish their tasks without being human aware. So in this scenario that I'm trying to show, there's this robot, and it's trying to help this human at this workstation area. And the robot's goal is to deliver items from inventory station to the human's workstation. And the human just works through whatever the robot brings it, and the robot has an idea for what human stress is. And human stress is when there's a lot of items in front of the human. If there's a lot of cluttered area in front of the human's workstation, the robot understands that's quite stressful for the human. And the robot's goal is to maximize productivity, and the robot's belief of productivity is how much stuff he brings to the human. So if the robot didn't care about the human, what would he do? He would just bring as much stuff to the human as possible, and it would make the humans really stressed out, and the robot would feel, I did my job, and it's up to you to do whatever you want. And so we want to model this interaction in some way. And also, the robot has other constraints. It needs to be able to move at a certain rate only. It needs to be able to charge its batteries. So if it doesn't have enough batteries, it knows it can't be productive. And if it can't be productive, it won't fulfill its function. And so, how do we model this idea? And we go back to this idea of the tank model that Orion mentioned earlier, and we can create a state model of the robot's belief about the world. So the robot has a belief of how much battery level it has a belief of how productive it is, and has a belief of the human's workload. And by thinking about the interaction between these tanks and modeling this as a dynamical system, as a linear dynamical system, we can put it in the same cost function and figure out what the robot's actions should be. So the robot's action could be left or right, pick up items from the inventory station, drop off items from the human workstation, charge its batteries.
Okay, great. Zoom in on the screen and you can actually see. So what we've done is...
Okay, we can try it again. We have arrows to show, this is the gaze focus point, so we'll do it again. Square with fixed head, and it's going to go to the point. And this is all minimum jerk, so it's minimum jerk between waypoints. 1, 2, 3, 4, 5. Okay, great. Okay, we're going to go home. And yeah, so that's directly using the minimum jerk stuff that Dr. Sennis talked about. But it was only in between, like intermediate.
You show the eyes staying straight and the head moving?
I just did that. Oh, well, we can do that again. Okay, we can do it here. You can see it here. So we're gonna, did we go home? Okay, I'm just gonna go home again just to be sure.
Show also zoom in to get the point.
Okay, well, I think you'll see it right here if I do it this way. And so now it's gonna be square with fixed eyes. So it makes, so here's the focus point is way out there. And then it makes a square. Well, the eyes are trying to maintain fixed. Okay.
And you can see that the head's moving quite a lot, but the eye position, it's focused way out and it's fairly stationary.
Right. Okay. So those are the minimum jerk behaviors. And of course we can make intermediate waypoints, but we didn't have time to do that because we wanted to show you some of the tracking stuff that we're working on. So I'm going to have Orion go up there at a particular spot. And here we see that Orion is being tracked, well not tracked, but it's being detected by the Kinect. And it's a people detection algorithm, and you can see that there's some, the point cloud is processed, and he's represented as green points, and there's a box over Orion. So what we want to do is that we want Dreamer to avoid Orion. So Dreamer doesn't care about Orion. Right. And this is exactly that, maximizing awkwardness behavior. Okay, so we're going to go home. And, all right, and the next thing we're going to show is that we can actually track Orion with just the eyes. So let's track Orion with just the eyes. Okay, well, you should guys see if it's actually tracking. Is it tracking Orion?
Yes.
Oh, that's great. Okay, great. And this is still just, the head is prioritized over the eyes. Okay. All right, now we're going to track Orion with both the eyes and the head. So yeah, so you see here, like it tries to find Orion, and these red, green, and blue points are the focus location of the head and 2 eyes. So right here, we're making 3 orientation trajectories over time, and so because we framed it in this whole body control framework where we have prioritization, we don't think about these joint positions of Dreamer. We just think about where we want Dreamer to look. And this makes it easy to command behaviors. So, I mean, we can even, yeah, so now we can just keep track of the eyes. Okay, but that's our demo, and
Questions? Because ultimately we lose a lot of ability of, and then we also build, skeletons and so forth. But the same could be done for the eyes and so on. What is our biomimetic way of looking at things? One of the things that is known is that our eyes move very quickly. It's called saccade. It's an Italian word. And that's, when this world has that, it has motors that are able to, swing back and forth, right? Mimicking that effect, because we believe that this is something that's going to contribute to the human-like behavior. So we do an effort. I don't think we have a general theory for all biomimetic behaviors, but scientifically speaking, we are not interested in having it all. We're interested in discoveries in particular kind of behaviors.
And long-term goal, in terms of like what are you trying to accomplish, like imitation over human body, such as like try to imitate a mechanism over like their muscles and their skeleton bones.
So I think I think anthropomorphic or how complicated the machine needs to be, I don't really care. What I care is about the word productivity, and whatever ultimately the design has to be to optimize productivity. Of course, productivity in today's environments, today city, home care, even conflict environments, you need more mobility, you need more manipulation, and you need some sort of human expression, because that's part of the equation of productivity, as we could see here, engagement and so on and so forth, okay? So anthropomorphic is a response if that embodiment is going to actually augment and maximize the productivity of whatever, negotiating with a person in a conflict zone, right? You have your robot being humanoid and dicing some of the feelings that we have for humans. That's going to be more productive, and so be it, okay?